and gentlemen, to my presentation on natural refrigerants in all application. Is it possible? This is a co-presentation with my friend Risto from Macedonia and myself. My name is Armin HAFNER. I'm a professor in refrigeration technology at the Norwegian University of Science and Technology in Trondheim. Welcome to this introduction talk, and the content today will be, after introduction, I will explain to you how we can utilize natural working fluids in different applications. And the main working fluids I will look into are CO2, R744, carbon dioxide, ammonia, R717, hydrocarbons, water, 718, and air, 729. At the end, I will give a short conclusion. So let's begin. The state of the art in many parts of the world are still F-gases, and these F-gases have made a severe impact on humans and our environment. This is a global issue. Still, we are facing problems with the ozone depletion. This has been, of course, mitigated with the Montreal Protocol. However, we are still seeing problems in this action, but it is on the way. That's a good news. However, global warming is a quite big issue with all these fluorine substances in all the different combinations and blends. However, the acidification of our drinking water by TFA because of unsaturated HFCs and HFCs is a big challenge for our human being on Earth. So, and also these poisonous decomposition products which end up in these pair and polyfluorinated acryl substances, which we also know as forever chemicals, is a big challenge for us. So this is a big hazard to the world from our society, from the refrigeration society. So we should contribute to not destroy the planet with these kind of fluids. And we know better that we can do. And then the big question is, what are sustainable working fluids to provide clean cooling? Let's see. So the substances up to the left based on methane, that is what we are used to. You see, we had this R12, R11, R22, R32 we are still using, depending on how many fluorine or chlorine are attached to the molecule based on methane. However, nowadays we are focusing much more on the propane-based refrigerants, where 1270 is representing propane, having not any fluorine, neither fluorine nor chlorine molecules or atoms on the molecule, while we don't want to have any ozone depletion. So that's why we cannot utilize these substances anyhow, because they have an ozone depletion. We are finished with that. And that's why people are looking into this 1, 2, 3, 4 substances which are defined in this direction. The more fluorine, if you substitute one of the hydrogen with the fluorine, you go down this line until you end up with only fluorine, the hexafluorine propylene. So along this way we have these substances. But are these the solution for the future? Probably not, because look, all this 1, 2, 3, 4 YF, which we all apply in the new cars, it completely transfers to HF and TFA, which accumulates in our drinking water. Not good. So this is not the solution. And the other alternative, also applied many times in chillers and other blends, is 1, 2, 3, 4 ZE. What does that do? Part of that, the 1, 2, 3, 4 is most likely to transfer into R23. And even if it's only 10% which transfers into R23, it has a huge impact on the global warming. So it's not at all that sustainable that somebody would like to have it. And there are also other breakdown products which are not healthy at all. There is more scientific experiments on the way, but we should be a precaution. We should take care not to see that this is a long-term solution. We should do different. And it is also the definition of this global warming potential, which is actually a challenge, because it is just based on what's in the fluid, what's in the bottle in the fluid. It does not take care what is included or what happened to the impact on global warming and also environmental impacts when the fluid was produced. So it's only defined as the substances in the bottle if that is released. And if it's a short-living substance, then on 100 years perspective, which is the definition of global warming, of course, this becomes a very small number. But this does not say anything about the impact on the environment, actually. And the decomposition is very dangerous, as we all know. Even when it starts to get in a fire, it's even more problematic. But even without the fire, all this impact to the environment. So that's why we should not just rely on the GWP numbers, which are ultra low by definition, but this is just a very narrow definition of some impact on global warming, but it does not at all account for other environmental impacts. So therefore, we should look at relevant natural working fluids, which can do a good job or even a better job in our sector. And as you can see, hydrocarbons are used, ammonia, carbon dioxide, water, and air at the bottom. These substances can be used, for example, CO2 in hot water heat pumps, mobile air conditioning. If you buy a new car, electric car, you can order a CO2 heat pump system. In commercial refrigeration, I will show you later, we have a huge deployment of these kind of systems all across the world. And especially in the food industry, CO2 is very much used when it comes to very low temperature, because applications down to -50 are no problem, which represent a very fast and safe freezing technology for a lot of food products. And lately, heat pump chillers have been developed. They can produce chilled water and hot water up to 90 degrees at the same time. And this is also a very efficient way to and utilized in hotels and other process plants. Ammonia is one of the eldest refrigerant, has been used all time in industrial refrigeration and heat pumps. But we will also see, I will show you some development towards larger, smaller systems with lower charge. Hydrocarbons, we all use them in our residences. Even now you can buy a split units with R290. Light commercial has been deployed all over the world with hydrocarbon in the bottle coolers and whatever in many shops. Transport refrigeration also utilizes a lot of hydrocarbons, propane mainly. We see some high temperature heat pumps where we can utilize the properties of both butane and propane in a very good way, so we can achieve 120, 130 degrees C, which is necessary in some applications where we have to reheat very hot water to sterilize and whatever. And home appliances have been transferred to hydrocarbons many years ago. Water has been used also very long time, since a long time, in industrial refrigeration and heat pumps, and lately also in data center cooling. Air can be utilized for low temperature applications below -50, as I will show you, and it has been also utilized in airplanes and trains for air conditioning. So the example for ammonia is that this refrigerant will stay also the next 130 years or even longer, because this is very energy efficient, and these systems nowadays also improve by doing a charge reduction and even improve the safety and tightness of these systems. That's why we can see more and more implementation of these units, for example in office buildings or as air conditioning, even at airports or exhibition halls. Cooling of data center is also a wide application for this refrigerant. And of course, industrial processes, cooling and heating. And it has been used even in the US for a very long time and still is in use. Here are some examples of packed low charge water-cooled ammonia chillers, just to give you an idea how these kind of units, how compact they can be built. On the right hand side we even see a two-stage unit for a heat pump system. So these are very nice example on low charge system. And this is another example of a charge reduction system. You can see that the ammonia part is in the middle of the unit, while CO2 is used to circulate it through the different evaporators, absorbing the heat, which is then recondensed in the evaporator of the ammonia system. By doing so, you can separate ammonia and food products and have a high safety in your production plant. And even the outer unit, they have a kind of doing a secondary loop on this part, so the amount of ammonia is rather limited, and still this is a very energy efficient system. So why is ammonia such a good fluid? Because it's globally available. It's very inexpensive and it has a very high, one of the highest energy efficiencies when it comes to this kind of chiller applications. And when you follow the regulation and the standards, for example, EN 378, ammonia applied as a refrigerant is very safe. Most accidents actually happen when it's handled as a fertilizer. So, propane was also 100 years ago, it was announced as the odorless safety refrigerant in the US. And still we are coming back now with this kind of hydrocarbon systems, which are very successful, especially in Europe, but also other parts in the world. You see, we have lots of different systems, small and compact system. They can be installed indoor or outdoor, depending on the size and the charge, of course. They are used for chilling, heating and hot water production. They have the integrated safety concepts. There are some requirements, you have to follow the standards, but then this can be very safe. And the explosion protection measures are done. And then depending on the charge, you have the restrictions where you can place it. And if you are just below 5 kilograms and have these kind of ventilated cabinets, you can place several of these units even indoor. Outdoor, you can even have more charge. I will show you some nice examples. And here is also the one example from the split unit, which got the first time ever a split unit got the Blue Angel award because of the eco-friendly air conditioning with the R290. So these are the large systems I would like to show you, just highlight some examples from a German installation. These are shopping mall air conditioning compressors or units, condensing units, 2 times 1.2 megawatt with only 40 kilo of propane on the roof of this supermarket shopping mall. On the right hand side you see a slightly smaller system, but only with 12 kilo refrigerant, 600 kilowatt of cooling capacity can be provided. And now let's go to water. Water has been introduced as a refrigerant in the very, very early days of refrigeration. A guy from Scotland in the early 1980s, in the 18th century, he artificially produced water ice by using an air pump system. Nowadays we are still using, in very large process plants, we are using still water as a refrigerant in steam jet refrigeration. We also use it in the absorption refrigeration systems, but also high temperature heat pumps are nowadays again applying water because we can utilize very high supply temperatures. It just depends on the compressor technology. You can nearly achieve 300 degrees C, which is very interesting in some high temperature heat pump applications to replace fossil fuels and provide steam or whatever with the heat pump. Here is an example for a data cooling chiller from a supplier doing this kind of compact systems which can be utilized. On the other hand, there is also, You see the size and the larger sizes of this example from ELK in Dresden, which there's a 1 megawatt chiller unit, which are located, or the real installations are done in several industrial applications across Europe. So this is possible. It takes a bit more space, but it is very efficient. When it comes to air, we can see these kind of systems, an example from Japan, where they store their valuable tuna fish at -60 or below, and this is very safe and natural, and the most advanced technology also, it does not need any heat exchanger inside or coolers inside the warehouse, which is very attractive for the operator of these systems. And these kind of systems, they do have a very high energy efficiency compared to traditional refrigeration vapor compression cycles at temperatures below -55, -60. So they're really energy efficient and safe. There's an example of a smaller system which is lately applied to store some vaccine at very low temperatures, and it was initially designed as a cryo sauna for people having some skin problems. But these kind of systems are very efficient. They have a turbo compressors and expander units, very sophisticated but oil-free, and as is mentioned here, they can be applied to very, very low temperatures. When it comes to CO2, you have seen maybe some installations already in your region. All across Europe, we have a lot of CO2 supermarkets, as I've shown on the upper right-hand side. I guess this number is soon approaching 50,000, because all the major supermarket chains have understood that this is the future. This gives them the highest payback time and the lowest operating costs. That's why they all shift to CO2. It's a long-term installation and a long-term refrigerant, because they know they can get this refrigerant anytime, all over the world actually also. On the left-hand side, I show you a heat pump chiller, which is utilizing the benefit of producing hot water at high temperature lift for heat pump, but also producing chilled water at the same time. And this can be very energy efficient if you utilize both the hot and cold side at the same time, which is actually, for example, quite interesting for a hotel where you need a lot of hot water, which you can store, and you need chilling of the equipment, rooms or kitchen or whatever. Lower left shows you a heat pump from a Danish manufacturer, developed to supply heat into the Danish district heating grid. And they're utilizing air as the heat source and bring in high temperature to the grid. Even VRV systems are possible, and there are many other applications. But most successful is also a heat pump for domestic applications in Japan. There are more than 5 million CO2 heat pumps in Japan, producing the hot water for many families in Japan. And lately also we see that the car industry is moving towards CO2, and they are introducing this in their new electric cars. So this is just a summary of the examples we have just seen on the previous slide. Hot water heat pumps, industrial heat pumps, supermarkets. Depending on the sophisticated systems are maybe utilized more in warmer regions, while in the Nordic countries a very simple CO2 system has been implemented more than 10 years ago, and all of the supermarkets are now soon finished replacing all the HFC systems with alternative refrigerants, either mainly with CO2, and some do have some hydrocarbon system, but none of them is continuing with the F gases. And heat pump chillers, as I showed you, is very attractive, especially also if you have a higher temperature difference on the chilled water side, the process plant. You can utilize a very interesting two-stage ejector solution, which is very energy efficient, very promising. So, in summary, we see here that in the different columns the alternative natural working fluids, which can provide a clean heating and cooling option, and they are available wherever you see the smiley. For the domestic application, we can see the CO2 heat pumps and the hydrocarbon systems are available in commercial refrigeration. For the large distribution centers, they use ammonia, else mainly CO2 and hydrocarbons. When it comes to industrial refrigeration and heat pumps, all of them are utilized except maybe air, but then water and space heat pumps are a good example for ammonia, hydrocarbons and CO2. Chillers the same, and in car air conditioning we see more and more CO2 systems, but there are also some alternatives utilizing hydrocarbons. So with this, I would like to answer the question we had in the beginning. Is it possible to do all these applications with natural working fluids? The answer is yes. If you do it, your customers will be very happy because they know that this is a technology they can rely on, and they can service, and you can service these systems even in 5 or 10 years because these fluids are available. And it is up to us. If our sector continues like with the blah blah blah, or if we do some action, because nobody will lose a job in our sector if we implement natural working fluid. Of course you can continue with the HFCs, blah blah blah, but you will be judged sooner or later. That's why let's go forward. Look at natural working fluids as the clean cooling solution, and we can do all temperature levels and applications with these fluids. There is really no technical barrier to replace current used synthetic fluorine containing refrigerants with natural working fluids. It's more about seeing the possibilities for you, your company and your end users than the ghosts when selecting the optimum refrigerant in the project or the product. But remember, of course, no single refrigerant can cover all applications. So that can be either ammonia, hydrocarbon, CO2, water or air. However, the group of natural refrigerants I just mentioned, they can cover all the applications which can be covered by the HFCs, but they represent dirty cooling. Remember, blah blah blah, this is not anymore. So, the fluorinated hydrocarbons, none of them can go as low in temperature or as high as the natural refrigerants. These fluids, they cover just the most profitable market in the middle temperature range. But when we look at this forever chemical pollution, we can see now register everywhere in the world. Our refrigeration sector has the possibilities to spearhead and complete phase out of dirty cooling. This can be our contribution to avoid that these forever chemicals are accumulating in the biosphere. And we can do this without compromising safety, food supply and human comfort, and nobody will lose the job. There is even more to do. With this, I would like to thank for your attention. If you have any questions, please get in touch with us. I wish you a nice rest of the conference and stay healthy and all the best.
Good morning, ladies and gentlemen. Thank you for having me today. I will speak today about why to use large industrial heat pumps and where they are used. I will also talk a little bit about air pollution and why we have to change. There is many reasons for changing, and one of them is actually air pollution. Why will it not change now? Not here. It's an urgent matter of transition because we have to comply to Paris Agreement and also to other pledges done by the EU and the global community. And we also know that the easy recoverable gas reserves, they range between 38 and 52 years, or perhaps a little bit more. It's really not to say now, but there is an end to how much gas there is in the ground. The fact is that it is dead animals from millions of years ago in the biologic mass that has been under big pressure in many years that has given us these fossil fuels. But they are coming to an end, and this day where it will end, it is not too far away anymore. We see declining productions of gas, declining production of oil, and so on, and we have to prepare for this scenario. In fact is also that the sooner we start, the better, because when we reach the day where it's all gone, then we have a big problem, and we cannot change so quickly. But we have now less than 10 years to 2030, where we have to cut about 30% of the emissions. We can also see here to the right of the screen the wind data. At the moment where I took the picture here, we used 50% of the electricity was supplied by wind in Denmark. The day before, the whole day, it was 67% in round figures, which was supplied by the wind. The 50% is taken at the very highest level in the mid starting of the day, where we use most energy. But we should have started the transition years ago, but it's better to start now than wait another year or two to find out something. We also see a growing price on energy worldwide. You can see this statistic from Ireland, Italy, Greece, Hungary, Germany, France, and Norway, where you see the prices are just going one way, and that is up. And this is a good reason for doing more efficient energy use and also use it better. A few definitions. Sustainable energy is energy that is defined, you have it for a given period of time, for example, gas, oil, coal, whatever, and then you use it. This is a sustainable if you can use no more than, and you can stay within a time frame. And that is really the definition of sustainable, because renewable is a totally different thing. It is when you have a resource that is naturally replenished with time. It means that it is a natural circling of materials, means, for example, wind or solar energy. Every morning when the sun gets up, you can replenish your batteries with solar power, and then in the night you can use it, and in this way you all the time replenish. Some sources can be overused, and then it becomes unsustainable. For example, geothermal power or energy can be overused. There was a city in New Zealand, Rotorua to be precise. They, some years ago, had used too much of the energy, and they could see that it was not good for the local tourist attractions, which was a geyser. It stopped jumping because they have pulled out too much energy, and that is unsustainable. So you can make some sources unsustainable, but if you adjust your use, you can make it sustainable and renewable all the time, because it will keep it going. You can say also that oil and gas is renewable, but then we should have started millions of years ago to put into the ground biologic material that could actually be there, and then in this way you could replenish. But it is not a real option, because we are not going to do it. And other things like uranium is not likely to be able to be replenished. Once it's used, it's gone, and that's it. You can say biofuels is a renewable source, and it can be counted as a fuel, but you have to not forget the environment and the air pollution that comes with burning. Any burning that has carbon in it and gives microparticles, and that is one of the problems we are facing. So the circular economy is a sustainable and renewable source because we have to use, instead of throwing out plastics, we have to pull it back and get it back in use instead of letting it end in the nature or in the big oceans where it becomes a pollutant. The benefit of electrification of the energy system using heat pumps from say 30 degrees centigrade and up to 250 is less particulate matter. I will come back to that in a moment. In the air means also longer lives for the individuals, less fatalities due to air pollution. We heard this morning Professor Todorovic talking about that we spent 95% of our time indoor, but still the fatalities are still high. I will come to the numbers in a second. And then more happy and so efficient employees and population in all. Air pollution is a matter that concerns everybody. I also saw that there has been demonstrations in Belgrade, so it is also a local problem. 4.2 million, according to the WHO, die from breathing ambient air. 4.2 million every year. And we have 3.8 million that die from breathing indoor air. That is very important. And it comes from burning wood, gas, whatever you have, fuels indoor for cooking and heating your air. So 91% of human beings are actually inhaling air that exceeds the WHO recommendations. And that can be avoided by proper and good use of our energy sources. Particulate matter means it is not a single pollutant, but it's a mixture and it's quite complex, and we actually don't know what we are doing. Let me remind you that in the 1960s, a big work was done to clean up all the rivers from all the garbage or whatever you say, all the surplus from our society went into the rivers, and the rivers were almost toxic to jump into. We saw that, and that was not good, and we cleaned them up, and today you can go and have a swim in most of the Europe rivers without risking your life. But still, we are polluting the air as nothing is happening, and we just do without thinking about it. But it's a complex mixture of solids and aerosols. It can be droplets of liquids. We don't know what it is. It can be dry fragments. It can be solid cores. It can be liquids of all types. It can be both inorganic and organic compounds. It can be metallic compounds and so on. So it is a problem. And why is it a problem? It's because you can divide it into two sorts. You have the PM10, which is particulate matters from 2.5 up to 10 microns. And then you have the PM2.5, which particulate matters lower than 2.5 micron. And you have also sometimes PM1, which is even smaller. And it is very important to understand that the PM10, they end up in the lungs, and you can have lungs of a teenager that look like an asphalt road. And PM2.5 goes into your body circuit where it does a lot of damages. It causes all sorts of things. For example, can give diabetes, it can give cancer, it can do infertility and a lot of other things. So it's really a big concern that occupies a lot of doctors and researchers at the moment. So the difference is the 10.5 and 2.5 PMs. It is about what they do to your body, and a lot of it comes from gasoline, from cars, oil, diesel fuels, and wood. Wood is always promoted as a safe and organic thing, but it produces a lot of small particles that are flying around, and therefore in some countries it is now becoming banned to burn just to warm up your house. You better use a heat pump, or you use the district heating if you live near that. PM10 can also be something that we are not so guilty about in the first place. It can be from deserts. I know sometimes in Belgrade you have desert sand coming from Sahara, but a lot of it comes from construction sites, landfills, agriculture, wildfires, waste burning. I've seen sometimes burning plastics and all this kind of thing. It ends up in your lungs and you die from it, and that is very important to understand, that we have to do something about it. Otherwise we are committing collective suicide. Just to show you a little bit about the size of these molecules, you can see a human hair is around 50 to 70 microns, a little bit depending on race and hair quality. And then you have the PM10 and you have the PM2.5, which is a fraction of a hair size, and you cannot see it. So sometimes when we see the air looks very nice and clean, it can be very, very dirty still. And there is a lot of causes, and you can study the slides after this conference, but you can see that PM2.5, they are also linked to premature deaths and also chronic heart and lung diseases and reduced lung functions for children. And that is a scary thing, because those who are to look after you when you grow old, they can be very sick when you need them, because they have been breathing the dirty air that we have been producing. Just to speed up a little bit, I will jump this one. So I will jump to what is important here, electrification and heat pumps, because it all about 50%, between 40 and 50%, depending on what source you look into, of our heat needs can be done by heat pumps, and it is one of the key technologies in the future. In the traditional systems, we had very often a boiler which emits CO2 and nanoparticles, and then you have also a lot of air that goes out through the chimney. And if you don't use that, it represents quite a lot of the capacity that you fire in from the gas or oil in the side, and then you heat up some water. On the other side, you have a heat pump which uses the electricity. It's a high value energy source, but it can be done naturally, and the heat pumps, they can produce heat very efficiently, and as well as cooling at the same time. It gives a very, very good efficiency that actually surpasses any boilers or electric heaters. So this is one of the good ways to do it. And in industrial applications, there are many places where you can use both the warm side and the cooling side, and that is a little bit the theme here. This is one of the heat pumps you saw Armin HAFNER just a moment ago showing a two-stage thing here, and this is one of them applied in a district heating system where they are using a local sewage and they boost it to 70 degrees. The 70 degrees is more to kill Legionella than actually needed for new houses. In Northern Europe, we designed the houses so you don't need more than 30 degrees, what we call floor heating. But if you also have to do potable water or tap water, then you need to kill the Legionella, and that is what they're doing here. So they are supplying at 70 degrees, so the end user out in the most far end of the network also can produce water at 60 degrees and kill the bacteria. Electrification of the grid is about avoiding burning fuels, regardless what it is, and heat pumps is a cornerstone of the new heating systems. We see in the northern part of Europe that it has been picking up very quickly, and in Denmark alone we have now installed more than 500 megawatt over the last few years. But IEA, the International Energy Agency, estimates that we need to install 500 megawatt heating capacity of heat pumps every month until 2050. So there's plenty to do for all of us. Nobody will be redundant, as also Armin Hafner confirmed just a moment ago, and to do the change. There is a lot of people working with boilers today, and there is around 129 million boilers that need to be exchanged to another kind of heating. So there is plenty to do for all of us, don't worry. This is a picture that has been used by the European Heat Pump Association, and it gives a good idea, but it's not covering all the possibilities, but just a few, where you can see that you have solar panels, you have underground heat source, you can use the rivers, you can use the sewage water, you can use the, the metro tunnels as a heat source, and you can use different industry heats. And of course, the buildings also need to be renovated to emit less heat during the winter and absorb more heat in the summer from sun, for example. Just to give you a picture of what we have done here in this part of the world, we have a heat pump system which simultaneously produce hot water and heating for space heating and cooling at the University Hospital here. And one of these units produce around 6 megawatt heating at the same time as we are doing some cooling. And there are 4 installed now, and there is space for one more if future needs one more. And in the same system, we have accumulation tank or vessel of 1,500 cubic meter. So we have a bank to make it run efficiently. Another one, this is the type of system Armin showed. It's a dual pack which can lift the temperature from the cold side and up to 82 degrees in this case, and it provides around 10 megawatt of heating capacity with a COP around 3, which is acceptable in this part of the world with the energy prices we have. With the growing energy prices, it becomes even better for heat pumps compared to other fuels. Here we have from another Danish company, Danfoss, where they have 4 units. Each unit is using waste heat, or not waste heat, but surplus heat from production side, which can be put into the heating system, where the hot water is then used both for sanitary purposes, but also for other things. And the heating capacity here is around 2 megawatt, or just around 2 megawatt. And under these conditions, it provides COP heating only for 4.2, but it will be higher if you can use both in the calculation. Let's go to one of the topics of the whole thing here, and it is about temperatures in what do you call it, aquatic center. Aquatic centers are very interesting because they can really use both the cold and the warm side. You can use it in different ways, of course, but this is one thing here. You also have to remind yourself, why is it that we are throwing out a lot of air from these buildings? Because some people, they think it is just about the humidity, but it's not only about the humidity, it's also about the chlorine in the water and over the surface of the water, because if you don't ventilate, the chlorine vapors over the water surface can become too high and unhealthy for humans. So that is one of the reasons that you are ventilating these aquatic centers. You also have some bleed off, and you have a lot of wastewater you can use, but just calculating on the air, it gives you, in this case, plenty of heat to fire back with a heat pump for the aquatic water. And the temperatures vary a little bit depending on the use of the water, whether it is recreational or therapeutic waters, or if it is for competition, it is a little bit lower and so on. Here we have a picture of one of them, and we found out that about 50% of the energy in the building was related to dehumidification and heating, and the other heats was 25% was used for heating the pool water and 25% for sanitary water. But you can see that dehumidification can be done by the cold side of the heat pump, and that is where it comes in that we can use both the warm and the cold side. The sanitary hot water in Denmark needs to be 60 degrees. I know in Norway they need about 65 degrees, and in other countries a little bit lower. So you have to check locally what is required for bacteria kill. I don't know if there's a difference between the bacteria, or is it what I call tolerance to the bacteria, but that is something that can be looked more into. Pool heating load can easily be covered by the heat pump and meet the requirements. In the dehumidification, you can take the cold water and dehumidify the water. The standard ventilation rate here is around 4. So, to sum up what we have heard until now, heat pumps, they can positively enhance the air quality in the future cities because we avoid burning fossil fuels. We can use wind energy, you can use solar power, you can use hydroelectric and all sorts of green, so you can clean up the air. And at the same time, with heat pumps, you can heat up your houses in the winter, so you don't need to freeze. It's not about freezing or becoming unemployed. There is work to do for everybody. There is also new possibilities. It's just, as Armin also said, to look at the positive sides and not so much as the negative things. And many more applications can be served by heat pumps as we move up in temperature. We are working currently now with temperatures up to about 120, but we will be moving up in the future. So with the working fluids with minimal environmental impact available, there is no reason for waiting. So what are we waiting for? Ladies and gentlemen, thank you for your attention.
Good morning, ladies and gentlemen. It's quite a great pleasure for me to have the opportunity to present. I want to compliment the two speakers before me for their very inspiring presentations. My presentation will be, I'm very sorry, less about technical solutions, but more about European policy and standards connected to the energy performance of buildings. I want to say a few words on what does the EU Green Deal and the programs like Fit for 55 reduction by 2030, and how do they drive the revision of the energy performance of buildings directive, and will this affect the use of the energy performance standards in Europe. My background is I'm chair of the CEN-TC 371 on the energy performance of buildings, the TC who coordinated the work of the development of the 50 standards on energy performance in buildings under the mandate for 80 and participating in ISO and CEN TCs on this same field. In my presentation, I assume that you are at least knowledgeable about the existing set of EPB standards, which I presented also in earlier conferences here in Belgrade. I'm very sorry not to be there real life, but I hope to visit Belgrade next year again. The Green Deal, the renovation wave, and so on, towards zero carbon emission by 2050. Well, we know that the buildings are acknowledged as one of the key focus areas for the European Green Deal, and more specific for the renovation wave strategy formulated by the European Commission. The ambition is at least to double the annual renovations of the European building stock, with a focus on deep renovation. And this is the basis for an urgent revision of the current EPBD that was published in 2018. And this to direct the national renovation strategies to achieve this decarbonized building stock by 2050. In the renovation waves, you can mention 3 focus areas: tackling the energy poverty and the worst performing buildings. This is to be aware of the fact that also the worst performing buildings are not very healthy. And the next thing is lead examples, priority for renovation, and because the public buildings should be an example, and decarbonization of the energy delivered and exported from and to buildings. The process of the EPBD revision is that a draft should be ready by the end of this year. And decarbonization is felt to be, by the majority of all the people who worked on the revision, as an urgent issue. We developed a standard in CEN towards the transparency of declaring the primary energy factors and the CO2 emission coefficients. This is a very important issue, as we try to, with using these standards, to make it more transparent how member states declare their primary energy factors and the CO2 emission coefficients for the different energy carriers. This standards provides a transparent framework to do so, and it specifies the choices to be made to calculate those values. And those values are very important when you declare the energy performance of a building. By using too optimistic primary energy factors or too low CO2 emission factors connected to the different energy carriers, you overestimate the energy performance, or underestimate, it is how you look at it, of your building stock. So it is very important to be transparent in this. The revision of the EPBD is also needed because currently you could say we have 27 plus national energy performance assessment procedures. This means that we are all claiming to follow the EPBD standards, but in reality, as we checked, we don't. Some countries follow it for, let's say, 80–90%, others for less. Comparing the outcome of the energy performance of buildings between member states is almost impossible because we don't know the real performance of their assessment procedures. They even didn't succeed in filling in the annexes A, which are included in all the EPBD standards, to show how which choices you made to do the assessment procedure. Because the energy performance recipe is actually, you assess the energy performance of a building based on a procedure where you have definitions, you have your calculation methods, you have your national choices, you have your in and outdoor conditions, and then you get your EP value. But what does it mean? For information, to compare buildings, yes, but how can I compare it between the different member states to show that we reach our targets if this metric is not clear? So for the metric, you could say this is the meter, the definitions and your calculation methods, and the reference you want to compare buildings, and you need to have and to know the meter to understand if the EP requirements are really met and can be compared throughout Europe. So, and it's clear to say, and I think very important to say, that the method you use for the energy performance certificates, they matter. Different conditions mean different EP values. That is, of course, obvious. But less obvious is the different definitions also lead to different EP values. And even less obvious, but also very true, different calculation procedures also lead to different EP values. And all these choices, well, not all, some of these choices are can be addressed in the national annexes. Example, if you use only an hourly method, you can really analyze the thermal comfort. So if there's no heating or cooling systems, there's no energy use, so you have a quite good energy certificate, but a bad thermal comfort. Only with hourly methods, dynamic interactions can be evaluated. Think of hourly energy needs and the heat pump system performance, or think of on-site produced PV and on-site electricity use from the grid or delivered to the grid. If you don't do that on an hourly basis, it doesn't make sense. A different method may have also incompatible and not to compare parameters. And different methods may also have limited range of coverage technology, which is a barrier for innovation. So there is a lot of discussion in Europe about the performance gap. And then they mean the difference between the calculated measured rating. The calculated rating is, of course, based on the user pattern, which is standard, the outdoor climate, and not a prediction for the real energy use of the building. This is difficult to explain to the people. The energy certificates based on the calculation are just to compare. And the calculation procedure, especially when it is based on monthly calculation steps, as is done currently in most of the countries in Europe, includes a lot of assumptions which may not be valid for all cases. The step to hourly calculation procedure is needed to address this performance gap and to limit it. And the EPBD should include requirements for this procedure. Well, at least at this moment, the expected new EPBD text requires an hourly procedure. How to make the EPCs, the certificates, more popular? Well, of course, it will help to address the performance gap. In the new Annex 1 of the EPBD, it gives an opportunity to use metered value to verify the correctness of your calculated energy use, also to use these metered values as additional information on your certificate. But also adding the requirement for the indoor environmental quality performance will make the energy certificate more attractive, because you can show the impact of absent or underperforming building systems. So you can have a high energy performance, but a low thermal comfort. Well, in the expected EPBD, this is softly addressed, not that strong as I wanted in Article 4 on the minimum energy performance standards or requirements, and Article 6 on the new buildings. There, in Article 6, indoor environmental quality issues shall be addressed, and this also can be done if you use the 2016 standard. The new expected EPBD is written towards improving energy performance and reduction of greenhouse gas emission for buildings, and it introduces some new elements. They don't speak anymore about NZEB, nearly zero energy buildings, but about zero emission buildings. I just make myself this with this symbol. Very high energy performance assessed according to the Annex 1. So first, reduce your energy need of a building, and then achieve a very low energy use, still needed, but fully covered by renewable energy sources produced on site. This is the concept that should be used. Then building renovation passports are introduced, providing a tailored map towards zero emission buildings, issued by accredited experts, followed by visits on site. This will be a delegated act in Europe by 2023. And this is a big step, because we really ask that the experts visit the building and give proper advice, and they should be certified and accredited. Sustainable mobility infrastructure is also a requirement. So if you build or deeper renovate buildings, you have to take care that there is a electricity infrastructure for cars and also bicycle parking. And then we think of smart charging and two-way charging abilities. And then renewable energy sources includes also now geothermal, we already know, but it is mentioned now, and ambient energy, which means that the appreciation of heat pumps is at a higher level. Deep renovation to zero emission buildings, only deep renovation, we call it deep renovation if more as 30% reduction is reached. There are definitions for useful and reference floor area according to the already developed overarching standard 52000. And many of those definitions in the EN ISO 52000 are taken into account in the new EPBD. Each member state shall set up a renovation action plan by 2025, with roadmaps and measures to be renewed every 5 years. Cost optimality, the Commission will revise the procedure by 2026. And on new buildings, they should all be zero emission buildings by 2030. And public buildings should give a good example by being zero emission buildings if there are new buildings by 2027. Also, the life cycle global warming potential has to be calculated according to the European Standard 15978 and reported at the energy performance certificates by 2027 for buildings bigger as 2,000 square meters and for all buildings by 2030. So also the embedded CO2 should be tackled there. And then indoor environmental quality shall be addressed as well for new buildings. The member states in Europe shall determine their energy performance on basis of an hourly calculation procedure step. This to take in account for the varying conditions that have a significant effect on the operation and performance of systems, indoor conditions, health, indoor air quality, and comfort levels. National methods shall be described according to those E and ISO standards, where we also included the indoor environmental standard 16798-1 and the standard on the primary energy factors and CO2 emission factors 17423. The energy performance shall be expressed in kilowatt hours per square meter reference floor area, where the definitions are also based on the 52,000. And the primary energy factors per energy carriers set by national authorities can be on annual, seasonal, monthly, weekly, or hourly. So it is still up to the, of course, the national authorities to report them, but on basis of this standard 17423. Another issue that also came up when we discussed with member states that they say, well, why not having a European software kernel to support the hourly approach? As this software should be based on the set of EPD standards and this very fully traceable and transparent, which is needed when you want to use this in the context of building regulation. It is also a great advantage when using the same tool throughout Europe and beyond, if wished, when defining the energy performance of buildings requirements and other EP requirements. That by doing that with the same procedure, the comparability will be much better. This software greatly facilitates the uptake of practical application of these standards and avoids that the same work has to be done over and over again in each country around Europe. Further, making a suite of high quality educational material, making the link to the software use freely available online will remove the last major threshold for practical application. So this is still a wish that is on the table, but we don't know if it's possible to achieve this. Already available, apart from the really software kernel, is, for example, a spreadsheet program that we publish freely available on our website from in ISO 15216. You can run this program with the same input data as needed for monthly procedures. So that's very easy. It is easier to understand and more transparent. It gives additional insight on hourly indoor temperatures and heating and cooling load of a building. And it calculates heating and cooling needs in the same calculation and reveals possible interaction. So the effect of nighttime temperature setbacks or on next day's cooling needs or monthly. And you see that in the current countries, where you have monthly procedures, there's no interaction. And that's why we promote you to use at least this spreadsheet program to analyze the behavior of your building. It's freely available, and it is of course not a software package, but it is something you can use at least to check the procedures used in your country. So my conclusion is, will the EPD revision have impact on the use of standards? Yes. There will be a more stringent policy regarding to the energy certificates. Their quality, their acceptance will be emphasized, the role of a correct use of the EPD standards. And an EU harmonized greenhouse gas matrix will make use of this 17423 standard, which will also harmonize the energy declaration of the different European countries, reducing the performance gap by improving the reliability of the calculated asset rating is supported by requiring the hourly calculation step. This hourly calculation step brings the use of smart readiness indicator to the next stage, where the building and the grid interaction will become visible and able to demonstrate the level of decarbonization of the energy used by the building systems. Thank you very much. If you want to know more about these standards, you can freely go to our website, where we provide a lot of information on the standards and also on the calculation procedures in the standard. There are freely downloadable Excel files and a lot of webinars and videos we produce to inform you and explain about the EPD standards. Thank you very much.